So let's look at the first example where we're going to start to deal with coefficients of friction and all that. So we have a 100 kilogram sled. It's on a snowy hill. We're told that the hill forms an angle of 23 degrees with the horizontal. So the sled just begins to slide downhill. We would like to determine the coefficient of static friction for the sled on the snow. So the key here is that just begins to slide. So right now we're kind of looking at that transition between static and kinetic friction. So just as it begins to slide, this is telling us we're looking at the maximum static friction. So for this, we're going to apply our knowledge of static friction. So once again, I like to sketch my inclined planes. I don't know why, I haven't figured that out yet, but it's just something I like to do. So let me draw my lovely little inclined plane here, 23 degrees, something like this. So here's our sled. So the sled wants to go down, or it's just beginning to slide down. That's going to tell us our force of static friction is going to go up the plane. So like everything with forces, we're always going to start with a free body diagram. So in this diagram, we're certainly going to have our force of gravity going down. We are going to have our normal force going perpendicular to that plane. And to oppose the direction of intended motion, we want to have that force of static friction. So this is our free body diagram. And of course, we can resolve the components of Fg. We can have this perpendicular component, and we can also have this parallel component. And as I mentioned earlier, once you resolve the components of the force of gravity, you should not be using Fg on its own. You're going to be using one of the components. So let's start by looking in the direction of motion. We're going to start looking parallel to the plane. Before we do that, let's set a convention. I'll say down the plane is positive, and I will say perpendicular to the plane is also positive. So we're going to start looking parallel to the plane. So parallel to the plane, we can write a net force statement. I can say the net force parallel to the plane. Let me look at all my forces that are parallel to the plane. So in this direction here, I have Fg parallel, and I have Fs. So I got the parallel component of the force of gravity and my force of static friction. Now, this thing is just beginning to slide, and we're looking at maximum static friction. So we're just going to assume V is 0, which also means that the net force is going to be 0. What that's telling us is our net force parallel to the plane. That's going to be 0. And then we have, our Fg parallel plus force of static friction. Now, we want to find the coefficient of static friction. Let's isolate for FFS first. So the force of static friction, we're just going to dump this Fg parallel to the other side. And we know some things about this. So the first thing is, we know the equation for the force of static friction. So we know the force of static friction is just going to be the coefficient of static friction times the magnitude of the normal force. And then we know that the force of gravity parallel, it's going to be this mg times sine of theta. So the objective here is to find the coefficient of static friction. We know the angle, we know the acceleration due to gravity, we know the mass. What we don't know is we don't know the normal force acting on this sled. And this is the key with, this is kind of similar to projectiles. When we did projectile motion, let's say you were looking in the x direction, kind of hit a dead end, you'd go to the y direction and solve for something to help you out in the x direction. It's the same thing with parallel planes. If you kind of run into a dead end in one direction, for example, parallel to the plane, what we can do is we can look perpendicular to the plane and we can see if something will help us out. So we're going to look at this direction that's perpendicular to the plane. And this is the first time that we've done this. So when we're talking perpendicular to the plane, we're looking in that sort of like y direction that's oriented perpendicular. So if I look at my free body diagram, my plane is running along this way. perpendicular to my plane is going to be this force, this normal force, and this force of gravity perpendicular to the plane. So perpendicular to the plane, I could say that the net force perpendicular is that normal force plus that Fg perpendicular. Now again, the object is not moving, so we know the net force perpendicular is going to be 0. In pretty much every single question that you do, F net perpendicular is going to be 0. The reason for that, the object may move parallel to the plane, but you shouldn't have something sliding and then suddenly it just starts to move perpendicular to the plane. For pretty much everything you deal with, F net perpendicular is going to be 0. So we know that the normal force plus the force of gravity perpendicular is going to be 0. Or we could just say that the normal force is the negative of the perpendicular component of the force of gravity. All right, we have a definition for the perpendicular component of the force of gravity. It's just mg times cosine of theta. Now, there's two ways you could solve this. You could certainly put this equation, you could certainly solve for this, 100 times 9.81 times cos of 23, sub that in here. I'm going to show you a simplification though. So first of all, we're going to divide both sides by Fn. So I'm going to get mu s is equal to this negative mg sine of theta divided by Fn. Or instead of Fn, let's put in this definition of Fn that we have. Because we know that Fn is negative mg cos theta. So let's put that in here for a second. Now the reason I've opted to do this, you'll notice that, well, there's a lot of simplifications here. The two negatives, they're going to cancel each other out. M and G are both going to cancel each other out. So all we're left with here is we're left with this ratio of sine theta divided by cosine theta. And you could plug in sine of 23 divided by cos of 23, you'll get an answer. If you don't know this, because it depends on what math course you've done up to this point, if you don't know, I'll tell you this, the ratio of sine theta divided by cosine of theta, this is actually equal to tangent of theta. So what we've gotten here is that this coefficient of static friction, it's actually equal to the tangent of the angle. But if you did sine theta divided by cosine theta, perfectly fine as well. This is a special case. Don't always assume mu s is going to equal tangent theta. That's a really, really, really special case. And this is basically only going to work with an object when you're dealing with static friction and the object, and that's the only, actually let me rephrase that. Basically it's going to be only apply when your net force is 0 and you're only dealing with a force down the plane, static friction, where static friction going in whatever direction up is going in, and then a normal force also included. You don't want to have anything additional like applied forces and all that, otherwise this is not going to work. But yeah, this is a very special case. So let's calculate that. What is tangent of 23 degrees? Well, the tangent of 23 degrees is going to give us about 0.424. So what we could say in this scenario, the coefficient of static friction between the sled and the snow, it's about 0.424. Again, doesn't have any units, we just present it as a number.